John Moore with JHM Technologies, here today to talk about the different acronyms of the molding processes that we are faced with day in and day out. We hear ones talking about these different acronyms, but truly what do they mean in the midst of the process itself? How do they differ? So let's go through the three that we hear so often. That is RTM, which is resin transfer molding, light RTM, which in effect is resin transfer molding with an additional light method of description to it, and then HP-RTM, which is a high pressure version of RTM. So what is the RTM process? Well, it's a process that we have two mold halves. So we've got a cavity half, which is normally the A side, the most concerning surface. It may be a male or it may be a female, but it's the A side. Then we have a given gap for part thickness. Illustrate that here. We've got a part that's cut in half. So we had an A side surface. In this case, the A side is the inside of this bin. Then we have a gap, which represents the part thickness, and then the B side, or contramold, or core half, or upper. There's all kinds of names for the second half of the mold. But in each of these three examples, there are two sides to the tool, providing for us in each of the three examples smooth surfaces, both inside and out, whether the A side is the outside of the mold or part, or whether it be the inside as it is in this case. The key is that we have a very uniform part thickness, very predictable, based on the part, or based on the mold cavity, and it has finished on each side. Indifferent than that of a open mold, spray up, chop type part, or even a vacuum infused part where we have the rippling on the back side. So really, what's the difference? Because today we think of RTM light as something new, and it's really not. The process, resin transfer molding, historically would have been inject in the center and have the resin flowing away from the center in a diverging flow path away to vents. If it were a square, just as I've drawn here, we would have a vent in each of the four corners. Again, taking that same part in its whole shape, if this were done in a conventional RTM sense, we would inject here, be it a mold in a male on the bottom, or if it were a female, that same point down in the bottom there, this area here, we would have injected. And then we would have placed a vent here, here, and then here at this side. So representing the same thing that we are in this square, the resin would have flown out. In that element of design, our concern is the fiber on the edge. If the resin gets to an edge and there's void of fiber there, then the problem is the resin can racetrack to a vent and leave a dry spot. It was the historic problem. When I say was, it still is today. But what we have adopted today, more than anything in anything that's changed, to say that something has changed, is when we go to the light RTM design. So what is the difference? Well, again, if we were molding that same square in a light RTM tool, the interesting thing here is, when I go back and I discuss this, what we're pinching or concerning ourselves to pinch that edge of fiber, because that, when you're running production in a mold design of this configuration, that'll cause you more scrap than anything. That is resin racetracking around the fiber pack and getting to a vent, and not then filling that void. Here, we create a resin channel all the way around. We ask the resin to racetrack around, and then we direct it to come inward to a central vent. So normally we have an injection port here, the resin's flowing around the cavity, and then converging to the vent, where we had venting here and injecting there. Truly, out of being in this industry for 35 years, if there's anything that's really somewhat different than we've ever done before, was when we started to build tooling in this configuration, because historically, like that bin, we would have injected in the center, vented at the corners, and focused all our design intent of the mold around how to pinch the fiber. Here, we didn't care about we asked the resin to racetrack around because we're going to converge here. And in another series, we'll talk about that converging path, how the advantage of that affects the air leaving the part. Very interesting. The other element that is different and why it can be added with the description of light is because we have this area surrounding the mold cavity of extra mold surface, which is a flange. In that flange, we will pull vacuum or create a vacuum. And that area acts as a clamping force. So we've got this perimeter clamping force that's typically 8 inches wide, or 200 millimeters in effect. This width here is where we're pulling as high a vacuum as our equipment is capable of doing, and it's clamping the mold together. We're also drawing a controlled level of vacuum on the cavity. So initially, we've got the entire mold aerial surface holding the mold closed in a clamped fashion. And as we fill, we then start to lose that advantage of vacuum in this area because we're filling it with the hydraulic force of the resin, which gets into another series of discussion about how to have your equipment control that flow rate, but that's not what this is all about. What we're going to talk about here is just the fact that the difference in the tooling is this clamping around the perimeter, where here we had to create full mold structure. And by injecting here in the center, it took even more pressure to force it to the edges. So when we consider the difference in the two, just in numbers, back in the day, as it were, when all the tools were built like this, you could easily say it was $1,000 a square foot. By using the advantage of vacuum, clamping it, eliminating much of the structure that we had at that time, we're able to produce tooling now, you could just round it off to say $300 a square foot. So that's the big difference. Okay, now we hear this buzz of high pressure RTM, brand new technology. No, it's not. High pressure RTM is in effect either a converging path, you can design the tool either way, a converging path or a diverging path. The biggest difference is the mold is left open, and typically this is, now here's another thing, high pressure RTM could be the mold fully closed and forcing at 1500 psi the resin to the outside to the vents. Typically the mold is left open, mill and a half, resin's injected, filling the mold with the volume of resin it takes to fill the part cavity, but yet obviously if the mold is slightly open, then when the mold fully closes, it forces that resin the rest of the way out. By having the mold slightly open, we can inject the resin in faster, put that slot of resin into that mold quickly, and then use the force of a press to form it and force the compression closing, as it were, forcing the resin to the edges. So the end of the story is here, the high pressure RTM, we can get speed, but we've got to have a press, and we've got to have solid tooling. We've got to have rigid tool set. Aluminum at minimum, typically it's steel. Here, we're generally talking about lower volume applications, ones that can use composite soft tooling, and that factor then, by using a converging flow path to the center, complemented with vacuum, drawing it as a clamping force around the perimeter, we can bring the cost of the tooling down and offer tooling that performs nearly as fast as it did back here at about a third the cost. So it's a little bit of today's tip on resin transfer molding. Thanks for watching.